Welcome to Lecture 1 of Engineering 310. In this first lecture, we will begin to talk about matrices, and this corresponds to Chapter 7 in your book. I believe in this lecture we will probably go beyond Section 7.1. I suspect we'll also cover part of Section 7.2, but whatever the case there, just look in the beginning of Chapter 7 of your book for the material related to this lecture. Now, a matrix is just an array of numbers, a rectangular array of numbers. So, for instance, one example of a matrix would be the following. Another would be something like this. And let's give one more example. Actually, we'll go two more examples. So here are a number of examples of matrices, and the first additional bit of terminology that we want to learn about is the idea of rows and columns of a matrix. When we look at, for instance, this matrix A, the rows of A are the horizontal lines. So the first row of A is 1, 2, 3. The second row of A is 4, negative 1, 2. And the third row of A is negative 3.407. The columns are the vertical arrangements of numbers. So the first column of A is 1, 4, negative 3.4. The second column of A is 2, negative 1, 0. And the third column of A is 3, 2, 7. So let me ask real quickly, and you try to decide for yourselves, and then I'll answer it. How many rows and how many columns does the matrix B have? Well, I hope you conclude that B has two rows. The first row is 1, negative 1, 0. The second row is 0, 3, 2. And B also has three columns. The first column is 1, 0. The second column is negative 1, 3. And the third column is 0, 2. Now, one way that we describe a matrix is in what some people would refer to as M by N format. That is, for instance, A is said to be a 3 by 3 matrix. M by N, in this case, is equal to 3 by 3. M is the number of rows, and N is the number of columns. And since both the number of rows and the number of columns for A is 3, we get 3 by 3. What is B? What are the dimensions of B? Well, again, M is the number of rows, and so that's 2. And we always put the number of rows first. And the number of columns is 3, so B is a 2 by 3 matrix. And on the other hand, C is a 3 by 2 matrix because it has 3 rows. The first row of C is 1, 7. The second row is 2, 1 5. And the third row is 3, 0. And it has 2 columns. The first column is 1, 2, 3. The second column is 7, 1 5, and 0. And then finally, the matrix V is a 3 by 1 matrix because it has 3 rows. The first row is pi, the second row is E, and the third row is 1. And it has 1 column, which is pi E1. So this is the way that we describe the dimensions of a matrix. And there's one more thing here that you should notice, and it's consistent with what your the kind of notation that your book is using. For a matrix that has just one row or one column, that is called a vector. For instance, in this case, this is a matrix with one column, so V is called a column vector. Let's just say, maybe do it like this. We'll say V is a column vector. On the other hand, we might have, let's say, perhaps R is equal to 1, 7, negative 3.2, and this is a 1 by 3 matrix, and it is called, R is a row vector. And one thing you should notice, and again, as I mentioned earlier, this is consistent with the usage in your book, for matrices that have just one row or one column, your book, since those are vectors, either column vectors or row vectors, your book uses lowercase letters for those. But for matrices in which both the number of rows and the number of columns is different from one, that's what some people think of as a true matrix, even though I want to stress that vectors are matrices too, but some people think of these as more, somehow more real matrices. And for these in which both the number of rows and the number of columns is different from one, your book is using uppercase letters. So this is just a brief introduction to what we mean by a matrix, to the idea of the dimensions of a matrix, and also the idea of a column vector and a row vector. And now let's proceed with this. And before we do, let me again emphasize that vectors are matrices. A column vector is just a matrix having only one column. A row vector is a matrix having only one row. So, can we add, so this is one question, can we add matrices together? And the answer is yes, but only if they have the same dimension. So all the matrices that we have used so far have different dimensions, so no two of these matrices could be added to each other. But let's maybe define a new matrix D, which is equal to 0, 1, negative 3, 4, 1, 2. And the first question I'll ask, and I hope you'll think about this for a moment and give it a try. If you need to stop the video, do so. But one and only one of the matrices above, of these 5 matrices that we have above, only one of them could be added to D. Which one is it? Well, I hope you concluded that the answer is B. The only matrix above that could be added to D is B, because B is the only matrix, is the only matrix above that has the same dimensions as D. As you can see here, D has 2 rows and 3 columns, so D is a 2 by 3 matrix. And if we look above, the only 2 by 3 matrix that we have above is B. So in order for us to be able to add matrices together, their dimensions, both the number of rows and the number of columns, have to exactly match. And so the number of rows in B is 2, as is the number of rows in D. Number of columns in B is 3, as is the number of columns in D. And so since there's an exact match on both the number of rows and the number of columns, we can add these together. And now we ask the question, well, what is B plus D? Well, B plus D is going to be exactly the same as D plus B. In other words, that's what they mean. They say that matrix addition is commutative. That means the order doesn't matter. And so B plus D, let's copy down. B is 1, negative 1, 0, 1, negative 1, 0, and 0, 3, 2. And D is 0, 1, negative 3, 4, 1, 2. And of course, we could write those in reverse order. We could say 0, 1, negative 3, 4, 1, 2, plus 1, negative 1, 0, 0, 3, 2. Just to emphasize that the order of the addition does not matter, and the answer will be, we just add up the terms, the individual terms. So the 1 plus 0 is 1, negative 1 and 1 is 0, 0 and negative 3 is negative 3, 0 and 4 is 4, 3 and 1 is 4, and 2 plus 2 is 4. And of course, you would come up with the same answer if you chose to add these two together. So here is your final answer for B plus D. And notice that this is also a 2 by 3 matrix. So in order to add two matrices together, their dimensions must match exactly, and then when you add them together, the result will be another matrix whose dimensions will exactly match those of the two matrices that you're adding. So that's how we do matrix addition. And let's just, this is, a very simple idea, but let's just pick maybe one more example. Let's maybe define a matrix G, which is equal to 1, 2, 3, 4, 5, 6. And so I'll ask which matrix above could be added to G and what would be the result. So please, throughout this course, I will frequently encourage you to stop the video and try to work something out for yourself. And I want to really just, get this over with now and say I really strongly encourage you to do that, because it'll give you extra practice that I think will really be invaluable. So I encourage you to stop the video for a moment and take a look and try to answer this question, and then come back and we'll all do it together. Okay, well, I hope that you had luck with this question. We noticed that G is a 3 by 2 matrix. It has 3 rows and 2 columns. And when we look above, the only matrix above that is 3 by 2 is C. So the answer is that the only matrix that can be added to G is C. That's the answer to the first question, which matrix above could be added to G. And now what would be the result? Well, C plus G, let's see what that would give us. C is 1, 2, 3, 1, 2, 3, 7, 1/5, 0. And G is 1, 2, 3, 4, 5, 6. And therefore, C plus G, we would have 1 plus 1 is 2. 2 plus 3 is 5. 3 plus 5 is 8. 7 plus 2 is 9. 1/5 plus 4, you could write that as either 4 and 1/5, or if you wished, you could write that as 4.2. Either one is fine. And finally, 0 plus 6 is 6. And so there you have C plus G. It is this matrix right here. And once again, notice that that matrix has dimensions 3 by 2, so its dimensions exactly match the dimensions of C and G. And so that covers the really straightforward idea of matrix addition. Now let's ask a second question. Can we multiply a matrix by a number? And a number is also frequently called a scalar. And the answer to this is yes. We can do this for any matrix. And the way that goes, let's just maybe pick this matrix G here. So G is 1, 2, 3, 4, 5, 6. And let's let the scalar lambda maybe be equal to 2. And so lambda G would be equal, when we multiply a matrix by a number, the result is just obtained by multiplying every entry in that matrix by that number. So since lambda is equal to 2 and G is equal to 1, 2, 3, 4, 5, 6, then lambda G would be 2, 4, 6, 8, 10, and 12. Or as another example, remember above, A was equal to 1, 2, 3, 4, negative 1, 2, 1, 2, 3, 4, negative 1, 2, and negative 3.407. And so lambda times A, we're still using the same lambda, 2, so we would get 2, 4, 6, 8, negative 2, 4, minus 6.8, 0, 14. And so again, we've just multiplied every entry of the matrix by the scalar under consideration. And that covers that extremely simple topic of multiplication of a matrix by a scalar. And so now the third question that I would imagine is occurring to you is, can we multiply one matrix by another? And the answer is yes, sometimes. And what we want to do now, and this will be the last big topic for this lecture, is let's try to understand exactly when we can and when we cannot multiply two matrices together, and also what we will obtain in those cases when the multiplication is allowed. So let's just say that we want to let's just say that F, we want to multiply the matrix F times the matrix S. And let's say that the dimensions of F are A by B, and the dimensions of S are C by D. Then we, let me rephrase this. The product Fs only makes sense if, I usually draw a little picture to help me remember this. B must be equal to C. In other words, the number of rows in S must equal the number of columns in F in order for us to be able to calculate that product F times S. Furthermore, the dimensions of Fs will be A by D. So we group we look at the two inner numbers and we ask, is B equal to C? I'll put a question mark. If the answer is no, if they're not the same, then you're just done. You can't even do the matrix multiplication. But if B is equal to C, then you can carry out the matrix multiplication, and the product Fs will have the dimensions A by D. So now that we've said all that, let's look at some examples. And we will also show how to calculate the product. So for instance, let's go back above. We have a couple of examples here, or one easy example here. We'll copy these matrices B and C. And we'll ask, does BC exist? And the answer is yes, because if B is 2 by 3, and C is 3 by 2. And these two inner numbers, we can check that off. They do match. And so the answer is yes. And BC will be a 2 by 2 matrix, because these outer numbers are 2 and 2. Now, the outer numbers don't have to match. Only the inner numbers need to match. But the outer numbers will tell you what the dimensions will be. Now let's ask, does CB exist? And so we'll write down CB. C is 3 by 2. B is 2 by 3. The inner numbers do indeed match. And what will be the dimensions of CB? CB will be a 3 by 2 matrix. And let's do a couple more. Remember that A is given right here. So I'll copy down A. We'll ask, does AB exist? Okay. Now A was 3 by 3, and B is right here is 2 by 3. And so, does this product make sense? The inner numbers do not match, and therefore AB does not exist. What about BA? Does BA exist? Well, BA, let's see, B is 2 by 3. A is 3 by 3. The inner numbers here do match, and so the product BA does make sense. And BA will be what will the dimensions of BA be? Well, it's these outer numbers, so it will be 2 by 3 matrix. So that's how we determine whether or not matrices can be multiplied together. We just need to look at those, at the number of columns in the first matrix and make sure that it matches the number of rows in the second matrix. But now we want to go back with each of these and try to figure out what exactly the product is. And let me show you how this is done. Once you see it and get the hang of it, it's very easy. So for the first one, we have BC. That's 1, -1, 0, 0, 3, 2. And then C is 1, 2, 3, 7, 1/5, 0. And the way that we actually multiply these together is that we go across the rows of the first matrix as we simultaneously go down the columns of the second matrix. Now, what does that mean? Well, we start going across this row and down this column. So 1 times 1 is 1. Plus -1 times 2, that's -2. So we have 1 plus -2 is -1, plus 0 times 3 is 0, -1 plus 0 is -1. Let's do that again. We're going across this row, as we go down this column. So when we multiply 1 times 1, we get 1. When we multiply negative 1 times 2, we get negative 2. And when we multiply 0 times 3, we get 0. So 1 plus negative 2 plus 0 is negative 1. So we multiply these terms and then add up the products. Now that we've calculated this number, now we go to the next one, which is obtained by multiplying this row times the second column. So we have 1 times 7 is 7. Negative 1 times 1/5 is negative 1/5. 0 times 0 is 0. 7 and negative 1/5 would be 6 4/5, or 6.8. Now we've multiplied this first row here by each column in the second matrix. So now we go to the second row, and we will just repeat that process. We'll go across this row and down these columns. So 0 times 1 is 0. 3 times 2 is 6. 2 times 3 is 6. 0 and 6 and 6 is 12. And now go across this row and down this column. 0 times 7 is 0. 3 times 1/5 is 3/5. 2 times 0 is 0. 0 and 3/5 and 0 is 3/5, or 0.6. And there you have your answer. And notice that, as predicted, the answer is indeed a 2 by 2 matrix. And that's how we do matrix multiplication. Now, we said earlier that CB also exists. And so I very strongly encourage you now to stop the video and calculate CB. Remember, C here is 1, 7, 2, 1/5, 3, 0. And B is 1, negative 1, 0, 0, 3, 2. So you calculate what we get when we multiply those two matrices together. And remember, you have the hint that the dimensions of the final result, the product, will be 3 by 2. So stop the video now and try this out, and then come back and we'll look at it together. Okay, so if we go across the first row of C, as we go down the first column of B, 1 times 1 is 1, 7 times 0 is 0. 1 and 0 is 1. Now we go this row times this column. 1 times negative 1 is negative 1. 7 times 3 is 21. Negative 1 and 21 is 20. And then finally, this row times this column. 1 times 0 is 0. 7 times 2 is 14. Okay? So, I'm sorry. Let me correct something that was written earlier. Okay. Earlier, when we were talking about this, we said CB exists because C is 3 by 2 and B is 2 by 3. And these numbers match, and so therefore CB does exist. But here I wrote down that CB is a 3 by 2 matrix. Obviously that's wrong. Remember, we get the dimensions of the product by looking at the outer numbers, and those outer numbers are not 3 by 2, but 3 by 3. So this is wrong, and let me correct that now. That's 3 by 3. Sorry about that. Okay, so now let's resume the calculation of CB. Okay, now that we've exhausted the first row, let's go to the second row. 2 times 1 is 2. 1/5 times 0 is 0. So we have 2 and 0 is 2. 2 times negative 1 is negative 2. 1/5 times 3 is 3/5. So we have 3/5 minus 2, so 3/5 minus 10/5 is negative 7/5, or negative 1.4. And then finally, this row times this column. 2 times 0 is 0. 1/5 times 2 is 2/5. So that's 2/5, or 0.4. And now finally, we turn to this last row. 3 times 1 is 3, and 0 times 0 is 0, so 3. And 3 times negative 1 is negative 3. 0 times 3 is 0, so negative 3. And 3 times 0 is 0. 0 times 2 is 0. 0 plus 0 is 0. And there is your result. And as we said a moment ago, this is indeed a 3 by 3 matrix. So you can see here, remember we talked about commutativity of addition, which meant that when you add two matrices together, the order does not matter. But clearly, matrix multiplication is not commutative, because BC is clearly very different looking from CB. It doesn't even have the same dimensions, so it clearly is not the same matrix. So in matrix addition, the order does not matter. In matrix multiplication, it is absolutely critical. Now, the final one that we'll do, I want you to do this yourselves. Okay, AB, you can't calculate that one because it doesn't, these inner numbers do not match. But BA does exist. Now, B, again, is 1, negative 1, 0, 0, 3, 2. And I copied A a moment ago. Let's see if we still have that available. Okay, so there's A. And let's just take that. Okay. So this is B. The first matrix here is B. The second matrix is A. And this product does make sense. So try to do this yourselves and then come back and check your answer. And remember that the answer here will be a 2 by 3 matrix. Okay, so I hope you had luck with that. Let's see how it goes. We're going to multiply this row times this column, and then that column, and then the last column. So 1 times 1 is 1, minus 1 times 4 is minus 4, 0 times 3, minus 3.4 is 0. So we have 1 and minus 4 and 0, which is negative 3. 1, negative 1, 0 times 2, negative 1, 0 would give us 1 times 2 is 2. Minus 1 times minus 1 is positive 1. And 0 times 0 is 0. So 2 and 1 is 3. And then finally, 1 times 3 is 3. Negative 1 times 2 is negative 2. 0 times 7 is 0. So we have 3 minus 2 is 1. And now we go to the second row of B. 0, 3, 2 times 1, 4, negative 3.4. Okay, 0 times 1 is 0. 3 times 4 is 12. 2 times negative 3.4 is negative 6.8. So we have 12 minus 6.8, which would give us 5.2. Then 0, 3, 2 times 2, negative 1, 0. 0 times 2 is 0. 3 times negative 1 is negative 3. 2 times 0 is 0. And 0 and negative 3 and 0 is negative 3. And finally, 0, 3, 2 times 3, 2, 7. Okay, 0 times 3 is 0. 3 times 2 is 6. 2 times 7 is 14. 0 and 6 and 14 is 20. And there is your answer, which is indeed a 2 by 3 matrix. And so that covers the main material we want to do here in Lecture 1, which is matrix. Well, we learned a little bit about notation. We learned about the dimensions of a matrix. We learned about matrix addition, scalar multiplication of a matrix, and matrix or the multiplication of two matrices together. And so now let's consider some questions for this lecture. Okay, so our problems for this first lecture will be as follows. Problem 1 will be 7.1.9 from your book. Problem 2 will be 7.2.11. And then in class we will have a problem 3, which will be another question covering the material from this lecture. And by the way, for this second problem here, there's a notation like this where you have a matrix and then you have a superscript of T. That denotes what's called the transpose of the matrix. And the transpose of a matrix is obtained by simply interchanging the rows and columns. So for instance, if R is, this is just an example here, if R is the matrix 1, 2, 3, 4, 5, 6, in other words, its first row is 1, 2, 3, second row is 4, 5, 6, then RT is the matrix whose first column is 1, 2, 3, and whose second column is 4, 5, 6. So notice that in this particular example, R has dimensions 2 by 3, because it has two rows and 3 columns, and consequently, the transpose of R has dimensions 3 by 2. So there's nothing more to that. Let's look, for instance, here. Here is B. B is 1, negative 1, 0, 0, 3, 2. So what would BT be? BT would be 1, negative 1, 0, 0, 3, 2. Or AT. Here is A. Just above, this is A, so AT would be 1, 2, 3, 4, negative 1, 2, minus 3.407. Again, just interchange the rows and columns. So that's what we mean by transpose. So once again, then, these are your problems, and what you need to do is I'll have you turn in these two problems. You're going to need to work on those, do some work, and just staple those pages together. Make sure to put your name on it, and you'll put that in one box. And then I'll have two boxes. You'll put this work in one box, and then in the other box you'll put this. I'll give you a sheet in class with this last problem on it, and you'll work on that problem and then turn that in as well. So that's the conclusion of Lecture 1, and good luck.